This video is on how we can remove salt out of our water. It also works on how you can remove calcium carbonate, iron, and many other things. If you watch the videos on the well house, you would realize that I'm not a very big fan of water softeners. Water softeners work by injecting salt into the system. People on sodium sensitive diets can often have health risk exacerbated by water softeners. Water softeners are generally, I'm of the opinion that they're generally misused appliances, and most people who get them don't really need them. So without any further ado, this particular video is on the theory and application of reverse osmosis equipment. At the heart of any reverse osmosis system is the reverse osmosis membrane. It divides a canister or area into two different pressure zones. You have a differential pressure about the semi-permeable membrane. This membrane has very tiny holes. These holes are so small that except for water and a few of the gases such as hydrogen sulfide, nothing much will transfer to the other side. So as we increase pressure on the water in the intake side, we will push water and very few gases to the other side. Hydrogen sulfide is one of the gases that will move over. So if you're looking for a reverse osmosis system to fix your sulfur water problem, you'll have to look elsewhere. It can't solve that particular problem, but it can solve calcium problem. It can solve salt problems. It can solve many other problems, iron problems, and other contaminants that are much larger. So if you were to put a great deal of this water that has the contaminants through the membrane, you would result in building up increasing concentrations of these contaminants as the water was cleaned and pushed over to the low pressure side. The industry uses a term for this highly concentrated water. They call it brine. And we need some way of getting this brine out of the high pressure side, else we would eventually clog and foul the membrane. So this is often done by a valve or some sort of a weep. Now here in this illustration I show using a little valve, and what this little valve does is he rotates and he holds that differential pressure for a period of time. Kind of steps through there, if you will. So if we need that differential pressure to be maintained in order to push the water through, we hold it and then we dump it, and then we hold it and we dump it, and as we do this, we repeat the process. We dump out that concentrated water that has those contaminants in it, and in this way the free-floating contaminants are washed out. Now you see the air gap flashing, and what an air gap is a way to keep your nasty drain contaminants from ever wicking back up into your clean system. It is a gap. It literally is a gap between a discharge point and a drain system. There is another type of thing called an air brake, where you may have a little bit more physical contact, but there's no possible way for water to crawl back uphill into that device. Now when you have a reverse osmosis, it's very important that you have your air gap or break in such a way that you cannot back siphon nasty germ-filled drain water into your filter system. If you were to go to your local home improvement center and buy a residential under-the-counter RO system, you'd likely see 3 containers or 3 jars. We've already discussed the center compartment, which is the RO compartment, but ahead of that, or in the lead position, is usually a pre-filter and carbon filter combination. Now what it does is, first, the pre-filter is used to mechanically screen large particulates to protect the membrane from the large matter, and then the carbon is used to take out any residual chlorine, because chlorine will affect the membrane. It will just destroy it. It'll eat it up. So that's usually in the lead position. Also, you'll normally have a tank, a small pressure tank for storage. Usually they're about a gallon, maybe a gallon and a half, or maybe even 3/4 gallons, something like that. And you'll also have, as an option, and most of them will have this, as a third canister, which will be just a pure carbon filter for buffering. Performance modifications. Let's first look at what we can do on the low side or the permeate side. These units normally come with a small tank, small storage tank. That's usually done so that they can fit under the sink. Well, if your rate of generation is sufficient, many times we find that we just simply don't have enough storage, because the way we use our water is only during breakfast, lunch, dinner, that sort of thing. We're drawing it down in small volumes over very narrow points of time. That gives our system an ability to recoup over time. But what if we don't have that situation and we have bigger demand? Maybe our 24-hour demand is such that we still have enough being generated, we're just drawing too much. Well, using a larger tank simply allows us to store more overnight and take care of that demand. Another way we can improve things is by use of what is known as a permeate pump. The way it works is we take the low side pressure, we drive it even further down by putting it to the suction side of a water-driven pump. We drive the delivery side, or the system side, up much higher, so we actually have a better delivery pressure at the sink, and we do it all by using the brine as the driving force. Much like a sprinkler has a water gong, we're using the brine, the wastewater, to turn the little water motor inside the permeate pump. It spins the motor and pumps the water. This creates an increased differential pressure and will increase the output of your membrane because it increases the differential pressure. High side modifications to increase production. Well, if increased differential pressure is the goal to increase production, then the easiest way we can do it is by providing a low volume, high pressure pump on the input. Remember, we're not actually generating much water in 24-hour period and in a 1-minute period and that sort of thing, but we do require a high pressure. The greater the differential pressure across that membrane, the greater the output will be. Well, what can we do then? Can we add the low side modifications as well? Well, certainly we can. The number one low side modification that we added was the permeate pump. It actually raised the delivery pressure as well, which gave us tremendous benefits at the sink. Also, the high volume storage tank adds a great deal to our project as well. The permeate pump also drops the low side pressure on the RO module. So what have we net done? We've dropped that low side very, very low, and we've raised the high side very high. And controlling this unit is simple. As long as we don't exceed the maximum working pressure of our under-the-counter system, we can even recycle the little 1-gallon tank. And we can use a low side pressure switch to drive that little baby pump. In short, we can operate a rail throughout the house, say at 30 psi, off that low side switch, let the little pump run off its built-in pressure switch at say 100 to 80 psi, whatever it's designed to do, assuming it's compatible with the rest of our system's working pressure, and it will pump up the little orange tank and cut off, and then that pressure will push against that membrane and it will cycle through until such time as we fill up our little gray tank. And when our little gray tank gets filled up to 30 psi, our rail reaches cutoff, the system cuts off, and we stay that way until we've used enough water out of our supply tank to require regeneration.